Welcome to this fourth of 5 webinars on Preaching with the Sciences, a project funded by the John Templeton Foundation. My name is Ed Foley, and I have the honor of being the project director for this pioneering program, whose work from the preceding 3 webinars is now posted online through the CTU website. The basic premise of this project is that the sciences have great potential for enriching the preaching of preachers, especially Roman Catholic clergy, although the sciences are infrequently employed in preaching. To close that gap, this venture places celebrated scientists and gifted homilists in direct dialogue with each other. A central outcome of this dialogue will be the development of over 100 homily outlines across the 3-year lectionary cycle, posted online in an open access format through the CTU website. These will hopefully aid preachers in exploring scientific resources in their own homilies. I'm very grateful to Rachel Kuhn, the Director of Development at Catholic Theological Union, for her presence today and her enormous help both in securing the grant and facilitating and producing these webinars. Thank you so much, Rachel. I'd like to introduce our gifted homilists, so central to this project, beginning with Deacon Greg.
Hi there. I'm Deacon Greg Kandra. I'm a deacon with the Diocese of Brooklyn in New York, New York. And most of my background is in communications. I was a producer for CBS News for a number of years, and I now work for Catholic Near East Welfare Association, CNEWA, a papal agency, as a writer and editor.
Thank you, Greg. Patrick.
Good afternoon. My name is Patrick Shebek. I'm the senior pastor at St. Paul Reformation Lutheran Church in St. Paul, Minnesota, where it is a balmy 40 degrees. And I also serve as one of the deans of the synod, as well as the synod's ecumenical officer.
Thank you, Patrick. Samuel.
Hello, I'm Father Samuel Hakim. I'm a Dominican friar and a priest living in Chicago, Illinois. And I am our province's director of vocations. So I work with young men who are interested in becoming Dominicans.
Thank you, Samuel. Gerald.
Gerald Loog, currently teaching worship and preaching at Princeton Theological Seminary, and I'm ordained in the United Methodist Church.
Thank you.
Live in New York.
Norman.
Father Norman, I'm a pastor of St. Basil Visitation. It's a Roman Catholic church here in Chicago, Southside Chicago. We are neighbors with CTU.
Thank you. Dan.
Dan Horan, I'm a Franciscan friar and a Catholic priest, and I'm on faculty here at Catholic Theological Union, where I teach systematic theology and spirituality.
Hello, my name is Father Matt O'Donnell. I'm a Roman Catholic priest of the Archdiocese of Chicago and the pastor of St. Columbanus Church in Chicago's Park Manor neighborhood.
Good evening, Father Adam DeLeon, Jesuit priest, working at Loyola High School in Detroit. Grateful to be here.
Hi, I'm Ann Garrido. I'm Associate Professor of Homiletics at Aquinas Institute of Theology in St. Louis, Missouri, and a former Martin Fellow in Homiletics at the University of Notre Dame.
Hi, and I'm Con Foley. I'm a priest in a parish 30 miles southwest of the centre of London, and I teach homiletics at the local seminary here as well.
Thank you. And besides these 10 homilists, we're fortunate to have a really terrific student assistant for the project. So Kathleen, would you please introduce yourself?
Hi, my name is Kathleen O'Brien, and yeah, I'm currently a student at CTU getting an MA in Systematics Theology, and I live in Hyde Park, and it's good to be with you all.
Thank you. We're delighted that we can have all of you with us. And now to our presenter. Dr. Grace Wolfe Chase is a professional astronomer who has worked since the 1980s in studying star and planet formation. Her PhD is from the University of Arizona. And after that, Grace received a series of postdoctoral awards, including the National Research Council and from the University of California, to continue her research and hone those astronomical skills. For a dozen years, she served at Chicago's Adler Planetarium, where her primary task was integrating her research and that of other astronomers with public education. This intriguing task, akin to a homilist's responsibility to integrate sound theology with the lived spirituality of the baptized, has sparked her engagement in what is known as citizen science. Specifically, she and colleagues are collaborating with citizen scientists in the Milky Way project that explores star and planet formation, aided by the discoveries of amateur astronomers. That research is posted on the website Zooniverse, which is the world's largest online platform for citizen science. Besides her current work as a senior scientist and senior education and communication specialist at the Planetary Science Institute, Grace also expends considerable energy and expertise building bridges between science and religion. This is something that she's been doing for decades through such organizations as the Zygon Center for Religion and Science and the Institute on Religion and Age of Science. She is currently vice president of the Center for Advanced Study in Religion and Science, and so she brings a wealth of experience in bringing together theologians and scientists, but always with an eye to the general public and their engagement as citizen scientists. So we're so delighted to have such a gifted researcher who is also deeply committed to the dialogue between science and religion as a participant in this project. Grace, you are very welcome, and the floor is now yours.
Thank you so much, Ed. So I'm going to start my screen share. First of all, I am delighted to be part of this wonderful series. Thank you so much. I've enjoyed all of the presentations you've had so far immensely. Today, we're going to be leaving the Earth, at least in our imaginations, and I'll be giving you a bit of a cosmic perspective on things. So as Ed told you, my area of research for the better part of 40 years now has been the birth of stars. So I also bring a historic perspective to this field. I'd like to start with a quote by Sarah Maitland, who says, "Natural history is not taught in seminary. This is curious, as most people in pastoral ministry are about 567 times more likely to be asked about cosmology or subnuclear physics or human biology or evolution than they are to be asked about irregular Greek verbs or the danger of the Patripassianist heresy." I am pleased to report that science is being incorporated into the curriculum of several seminaries at this point in time, and I am delighted that there's interest in bringing science into homilies as well. So I think it's important for you to know a little bit about who I am, not just what I do. So I'd like to begin with a story that interweaves the two and illustrates some of the experiences that led me to where I am today. First of all, I come from a very small all-female family. I was born in New York City and raised in New Jersey by my mother and maternal grandmother. Informal education played a larger role in my than formal education did in steering me towards a career in the space sciences for a number of reasons. My passions during childhood and adolescence were figure skating, astronomy, and science fiction, and particularly Star Trek. I'm a hardcore Star Trekker. I think it's important for people to see other people who remind you of yourself playing diverse roles in society. And for me, science fiction did that during a time when all the astronauts were male and advertisers were marketing space-related toys exclusively to boys. I was raised Lutheran, and I currently use science fiction a lot to help stimulate science and religion discussions today. So my journey continued at Cornell University. I was inspired to attend Cornell by watching Carl Sagan on The Tonight Show with Johnny Carson. With my mother, when I was in high school, we loved to watch Carl Sagan on The Tonight Show with Johnny Carson. And I went to Cornell University, and the first thing I experienced was culture shock. So at the time, the male to female ratio was very high across the entire arts and sciences school. And as far as physics majors went, well, there was me. Some of you may know that Andrew Dixon White was the first president of Cornell University. and he wrote what has become a rather notorious treatise on the history of the warfare of science with theology and Christendom, which was extremely influential in promoting what's become known as the conflict thesis between science and religion. It's still widely popular among critics of religion today and the general public. So that by the time I graduated from Cornell, I almost got the sense that the word scientist and the word atheist were synonyms. My mother died when I was 19, and at that time, I had to take a long leave of absence from Cornell. Some really good friends helped me to tend to my grandmother and get back to school after a few years. And I'm forever grateful to them because that really started my journey in astronomy. I was very fortunate in my senior year to have a great mentor whose recommendation I'm sure helped me get into many of the top-notch graduate schools to which I applied in astronomy. So my journey continued in graduate school at the University of Arizona. And I began in the 1980s when I began working with one of the pioneers in the field of star formation. At the time, studying the birth of stars was a nascent field of study, since the telescopes that we use to study the cold, dark interstellar clouds of gas and dust that can collapse through gravity to form new stars only came online during the late 1960s. So here are just a few of the telescopes I've used over the years. So these instruments collect infrared light and radio waves at the wavelengths that probe the conditions of cold molecular clouds and let us study how the densest regions of these clouds give birth to new stars. So let me tell you what I mean by densest regions. These dense regions in space are still about 100 trillion times less dense than air at the surface of the Earth. So not very dense. I used the telescope in the upper middle there to carry out my dissertation. And several years ago, my family and I got to witness its destruction, sadly. There's a new telescope that currently takes its place, so it's not all bad news. Also at the University of Arizona, it was my pleasure to come to know the Jesuit astronomers of the Vatican Observatory, some of them who I've known for nearly 4 decades now. These were the first people that I'd met who really thought deeply both about their faith as well as their science. And they've greatly influenced my own thinking over the years. I think it's so important for faith leaders to encourage talented young people to consider careers in the STEM fields for many reasons. We need bridges between the worlds of science and religion. We need people who can speak both languages, and we need to empower the next generation of scientists who can use their skills to improve conditions in their communities and around the world. So I just wanted to highlight a few publications by Brother Guy Consolmagno, the current director of the Vatican Observatory. 2 books I can't recommend highly enough: Brother Astronomer, Adventures of a Vatican Scientist, and Would You Baptize an Extraterrestrial, and Other Questions from the Astronomer's Inbox at the Vatican Observatory. So if you want some good story leads, check out some of Brother Guy's books. So as I mentioned, I've been at the Adler Planetarium for a long time. After graduate school, I was awarded a couple of postdoctoral scholarships to pursue star formation studies, first at NASA Ames in the Bay Area and later at UC Riverside. During my first postdoc, I was prolific in another way. I gave birth to 3 children in 2 years. Those last 2 were fraternal twins, by the way. The person I worked with there, I think, still laughs about this. Can't believe that that actually happened. And by my second postdoc, I began to wonder whether I wanted to go the traditional academic path that my advisors in graduate school drilled into me continuously. They felt that it was the only respectable path for a scientist who wanted to do research. Well, about this time, I saw a position advertised combining academic research with education and public outreach at the Adler Planetarium in Chicago. And I recall thinking, this is perfect for me. This job description was written for me. I knew I wanted to continue to do research, but I also wanted to give back to society. And informal education had played such a large role in my own development. I also found that formal education isn't always very inclusive or friendly to diversity. But this position allowed me for 22 years to involve my family in various different ways in my career. And over the years, integrating research and outreach took a specific form in citizen science, which Ed told you a bit about, and I'll say more about citizen science later because I think it can play an important role in faith communities. So this was a pivotal moment in my life. At about the time I began working at the Adler, a letter appeared in Nature that really profoundly influenced my passion for outreach among religious communities and led me toward a number of academic organizations devoted to science and religion dialogue, as well to public forums for science and religion. And I started doing a lot of outreach. The letter had the title, Leading Scientists Still Reject God. And without going into the details of this article, it just became very clear that we need much better lines of communication between different communities. I also noticed that my kids, as they were growing up in Midwestern suburbia, very often when they expressed enthusiasm for science to their classmates, they were often told, well, you like science, you must be an atheist. Well, we were very fortunate to find a religious community where I didn't feel like I had to hide my field of research, but I was repeatedly invited to teach adult education classes on astronomy, which were really enthusiastically received. I've been very, very pleased with that. Lest anyone think that this conflict is a problem primarily for a certain subset of evangelical communities, it's not. It's far more widespread than that. And I think part of the reason for this is that many religious leaders just don't address science, period. And that kind of feeds this notion that science and religion are in conflict. So, segueing to the story of our universe. The story of our universe begins roughly 13.8 billion years ago. And if you compress that 13 billion year history onto one Earth year, then 1 second on the cosmic calendar is about 500 years. This big history is accessible to us because of the finite speed of light and because we live in an expanding universe with a finite beginning. The implications of this are profound. At our point in time, we have a fossil record of the past in the light that comes from us, that comes to us from faraway places in the universe, similar to the way there's a fossil record in the geological layers of the Earth. Now, this allows us to probe, explore how the universe and its contents have changed over time. Now, a couple of things to note on this cosmic calendar. First of all, our solar system doesn't even form until the month of September on this cosmic year. And basically all complex life develops during the last month of the year in December, with all of human civilization being compressed into the last minute before midnight on December 31st. So this is something to keep in mind during my talk, that we're talking about an immensely old, immensely large universe. I'd like to take you on a quick tour through space to get an idea of how some of these timescales and distances relate to each other. I'm probably the only one, or one of the few of you, who can actually remember when this photo was taken by the Apollo 8 astronauts on Christmas Eve in 1968. And how our jaws dropped as we saw our planet looking like a blue and white marble in the distance. Now, the Earth and the Moon are separated by about 250,000 miles, 250,000 miles. It takes light a little over a second to travel that distance between the Earth and Moon. This may seem like an enormous distance, but let me tell you, I had a very long commute for 22 years. And if you had a commute like I had, you can easily drive this distance over the course of your career and even further. However, you won't get much further out into the solar system. So what you're looking at here is the solar system, not to scale. When I talk about the solar system, I mean the sun and all the worlds, planets, comets, asteroids, dwarf planets, all the worlds that orbit the sun. Now, the speed of light starts to become very important in considering the transmission of information and communication. The distance between the sun and the earth is roughly 93 million miles. And it takes light 8 minutes to traverse that distance. And what this means is if there's a flare on the sun that occurs this instant, we don't know about it for 8 more minutes. For light to travel from the sun out the radius or so of the solar system, about 5 billion miles, now we're talking hours to get to Pluto and these Kuiper Belt objects. But the solar system is still very small compared to the average spacing between stars. So the sun is a star. Stars come in different colors, temperatures, sizes, masses, and brightnesses. They're typically spaced by tens of trillions of miles. So we use this unit of distance called the light year, where 1 light year is roughly 6 trillion miles. Okay, not million, not billion, but trillion miles. For most of their lives, stars are powered by nuclear reactions that fuse hydrogen into heavier elements at the enormous pressures and temperatures deep within their cores. Around 70% of all the stars are stars we call red dwarfs. These stars are intrinsically tens or hundreds of thousands of times dimmer than our sun. 50 of the 70 nearest stars are red dwarfs, but you don't see them in the night sky because they're so dim. You tend to see the brighter stars in the night sky. And on the other side of the brightness spectrum, there are very luminous blue stars that are tens of thousands of times brighter than our sun. And these stars make up only less than 1% of all the stars out there. But these stars are extremely important because through the course of their lifetimes, they fuse heavier and heavier elements at their cores and eventually explode after millions of years and seed interstellar space with the heavy elements that are necessary, for example, for life. None of these luminous blue stars are in the solar neighborhood. As I said, they're rare. Over the past 25 years, we've also discovered thousands of planet-sized worlds orbiting other stars. Now, we call these planet-sized worlds exoplanets. You'll hear me also call them planets because they are planets. They're just planets that orbit stars that are not our sun. The nearest potentially habitable exoplanet actually orbits the closest star to us, a star called Proxima Centauri, which may be part of a system of 3 stars, the Alpha Centauri that you see in this diagram here. And I'll be saying a little bit more about planet habitability in a little bit later on. Now, our sun is one of roughly 400 billion stars, give or take, in a large group of stars we call the Milky Way galaxy. If you've ever been to a dark sky location, you may have seen the Milky Way in the night sky. When you look at the Milky Way, this band of light in the night sky, you're looking into the plane of our Milky Way galaxy. This is our picture. This is what we see. The stars you see in the night sky are a very small fraction of all the stars in the Milky Way. The picture on the right, we never see our galaxy like this. We infer its shape by making various different kinds of measurements from our place in the solar system, which is located roughly halfway out. So if the center of our galaxy is the galactic city, then we're sort of in the suburbs, halfway out towards the outskirts of our galaxy. Our galaxy is about 100,000 light years in diameter, which comes out to, this number is 600 quadrillion miles. And so you need to remember that when we look out in space, to look out into space is to look back in time. We never capture the universe as it is now at this moment in history. Now I'm going to take you a little bit further out into space. Our nearest, the nearest galaxy that has more or less the same shape as our galaxy, the Andromeda Galaxy, is 2.5 million light years away. On a clear moonless autumn night, you can make a smudge in the constellation of Andromeda. That smudge is the only galaxy beyond the Milky Way that you can actually see with your naked eye from the northern hemisphere, although you won't see it like this with binoculars or a small telescope. But if you can spot that smudge, think about this. The Andromeda Galaxy and the Milky Way Galaxy are actually approaching each other because of their mutual gravity. And they're predicted to merge and form one big, huge galaxy several billion years from now. When galaxies merge, the individual stars don't collide because a star might be 1 million miles in diameter, but the typical spacing between stars is tens of trillions of miles. So I'd like to point out that 2.5 million years is still only an hour and a half on our cosmic calendar. We'll go out further in the universe to see some galaxies that are a little further away. Galaxies are very diverse. You can see some of the different shapes here in these galaxies that are tens of millions of light years away. Beautiful examples. The Hubble Space Telescope was still able to make out many details in these galaxies. And these fuzzy pink patches that you see in the antenna galaxies, which is an example of a merging pair of galaxies. You can also see these fuzzy pink blotches in the Whirlpool Galaxy. Those fuzzy patches are actually hot hydrogen gas lit up by luminous young stars. And we'll see an example of this in our own galaxy much closer to us, where young stars are forming today in a few minutes. So let's go a little bit further out to one of many ultra deep fields that the Hubble Space Telescope took. And let me tell you what you're seeing here. Looking away from the plane of our galaxy in seemingly empty patches of sky in our Milky Way, this image is only about 1/10 the size of the full moon in the night sky, and yet it contains nearly 10,000 galaxies. The only stars in our galaxy that you can see in this image are these bright points of light with these crosses. They're diffraction spikes, they're optical effects. In this view, the brightest galaxies you can see are about 1 billion light years away, and the smallest, dimmest, reddest are at distances of about 13 billion light years. So here we're seeing a view that spans most of the history of our universe, the furthest galaxies here being the light coming to us from a time when the universe was only about 800 million years old. Going out a little bit further to the Hubble Legacy Field, this field of view is actually the size of the full moon. I know it doesn't look very interesting because all of these galaxies look like tiny little points of light. Let's zoom in a little bit more. And in this Hubble Legacy Field, in the entire legacy field, there are roughly 265,000 galaxies, stretching to look back times that correspond to about 13.3 billion years ago, 500 million years after the Big Bang, when stars actually at this period of time had been forming and galaxies were still assembling. So here's kind of a neat thing to think about. In the part of the universe we can observe, which isn't the whole universe, the universe itself may be infinite, we don't know. There are about 100 billion galaxies, with estimating about 100 billion stars per galaxy. That gives you the number of stars in the observable universe, 10 million quadrillion. That's a 1 followed by 22 zeros. And we now have reason to think that there may actually be more planets than stars in the universe, and that many of these planets might actually support life. So let's look at why we think there may be more planets than stars, and let's think about the prospects for life elsewhere. So I'm going to go back a few hundred years to a hypothesis of how our solar system formed. Astronomy is typically a theory-driven science. And what we mean by this is that many phenomena were predicted to occur in space based on known physics at the time, well before we had the technology to actually go look for them, to actually observe them. The origin of the solar system is a great example of this. Pretty much using only Newton's universal law of gravitation and some easily observable features of the solar system, like the planets lie more or less in a plane, and they orbit the sun in the same direction. The philosopher Immanuel Kant and Pierre Laplace, the physicist, came up with this hypothesis that maybe our solar system started with a huge cloud or nebula in space that was spinning, and as gravity pulled it together, it flattened out, and the sun would have formed at the center of this huge pancake or this huge nebula, this huge protoplanetary disk, with the planets forming in sort of the outskirts of this disk. Now, there was very little to go on at the time. This was only a hypothesis for hundreds of years. We had no way of actually observationally investigating this. And of course, we still can't turn the clock of time backwards, right, and observe our solar system being formed. We can, however, use technology for hints of our solar system's birth. And we can do something else. We can search space for places where stars and planets continue to form. So let's go now to the beautiful winter constellation of Orion, and particularly to a little fuzzy pink patch here known as the Orion Nebula. This fuzzy pink patch corresponds to is the same sort of deal, those fuzzy pink patches in the galaxies that I showed on previous slide. But the Orion Nebula isn't millions of light years away. It's a mere 1,400 light years away. And the Hubble Space Telescope got a very deep view of this nebula and the young stars within it and studied it in great detail. And these objects have been since studied in great detail over the past few decades. So this is a mosaic put together by the Hubble Space Telescope in 1994. And all of these little dark objects you see pulled out here are called proplids, standing for protoplanetary disks. There was early evidence, and that evidence mounted over the years, that there are actually planetary systems around other stars in the process of formation. This nebula is lit up by these actually more than 4 of these bright stars that I was telling you about earlier, that are the type of stars that end their lives in these supernova explosions. And within this entire cluster of stars, there's something like 800 stars. Now, we have good reason to believe that most stars actually form in clustered environments. And we have evidence that our sun formed in an environment where a supernova explosion went off as our planetary system warming. So we think our solar system was born in an environment like this. So this environment is far more complex than the more simplified way of thinking about a cloud collapsing through gravity. There are all sorts of processes that are important. There's turbulence in the gas, magnetic fields, radiation pressure, and these play out over enormous scales, time and space. And just as we might say that siblings compete for things like food in the biological world, stars forming in clusters compete for gas to gain mass, to get bigger. So word from biology like nature and nurture very well metaphors for how stars and planets develop. Over the last couple of decades, we have finer and finer detailed, higher resolution observations of disks like the ones in the Orion Nebula. And most of these disks see here are not visible light images. These were put together by an array of radio telescopes in Chile. The acronym is ALMA. And you can see all these beautiful structures in these disks. They almost look like the grooved old records that only some of us are old enough to remember. And these gaps here, there is evidence that these gaps form when planets to form within these disks. And you get all sorts of intriguing spiral arm patterns and such. So we're building up the number of these protoplanetary disks that have been observed at high resolution. So over the last 3 decades, we've assembled a general picture, and this is a highly simplified view of how you go from a collapsing cloud to a system with a star and planets. This picture was put together from many different observations over many wavelengths, not just optical, but infrared and radio, and over huge scales. The clouds that collapse to form stars are trillions of miles across. The resulting planetary systems are billions of miles, and a star itself is only 1 million miles or so in diameter. So this is very simplified, as I said, and I'm not sadly going to talk about bipolar outflows at all, except to say that when I first started in star formation research, this is what I was concentrating on, mapping out these bipolar flows that are huge. We actually in the 80s used them as proxies for disks because a bipolar outflow can be light years in extent, much larger than these disks that actually generate them. And in the 80s, we had no way of imaging the disks directly. So at the same time, we've been learning that stars and planets form together. We've been conducting vast searches for mature planets orbiting mature stars. And over a similar period of time, we've observed thousands of planets, literally thousands of planets orbiting other stars. So what you're looking at here is a histogram plotting the cumulative number of these exoplanets that have been detected over the years. Over here on the left, these are the different methods that are used. Clearly, we don't have time to talk about all of these methods that are used to detect and measure properties of these planets. But I will show you how the transit method works. It's been one of the most prolific methods used. And it works by the fact that in some cases, the orbits of planets around their stars cross the face of the star, and we can observe a dip in the output from a star when that happens. Now, I have to tell you that the diversity of worlds and planetary systems that have been discovered rival the worlds that were conceived by science fiction writers for so many years. You get some huge planets in star-hugging orbits very close to their stars. We've discovered exoplanets in systems with 2 or more stars orbiting each other. And in fact, the first planet orbiting a binary star system was nicknamed Tatooine in honor of the Star Wars world so long ago. And I could share stories that could go on for hours. So if you want to have a beer sometime, we could talk about all of the wonderful diversity of worlds. I don't have that much time, but I do have time to show you an artistic depiction of some of that diversity. So what I'm going to do now, so you can hear this, I'm going to unplug my headphones and take you to a YouTube video and tell you a little bit about what you're seeing. So this is an orrery. An orrery shows you the orbits of planets around stars. You don't see any stars here. The solar system, the orbits of Mercury, Venus, Earth, and Mars are to scale with other orbits depicted here. The sizes of these planets are not to scale by any means. And these planets are color-coded with the scheme that you see over here on the left, such that hotter planets are colored redder, bluer planets are cooler. And those temperatures are based on how far away the planets are from their stars and how hot their stars are. So this just is a visualization that I love it. I think of it as the marriage of art and science. It gives you a sense for the diversity of planetary systems that have been discovered. And so from here, so I'm going to show you another quick video. To go to that, we don't have to go to the web this time. So there's a particularly interesting chain of Earth-sized planets in a system known as TRAPPIST-1. And as I play this video, I'm going to let you read the captions rather than talk over this, so you can see get a sense of what's going on in this system. So you'll be noticing that even the outermost planet in this system takes only 21 days to orbit its star. For comparison, it takes Mercury, the closest planet to our sun, 88 days to orbit. This is kind of like a mini planetary system, but since the central star is so cool and dim, there are actually about 3 planets that are in the so-called habitable zone of this star. A little bit more about that in a few minutes, but first I'd like to take you to one more website. I know some of you are musically inclined, and if you want some mind-blowing harmony music of the spheres, there were some talented musical astronomers that actually put the orbits of these planets to sound. So the orbits of these planets, the periods of these planets are in integer ratios of each other, which form this beautiful system of harmonic resonances. Over the 7 planets, all of those orbits are in integer ratios of each other, and they form this harmonic chain. So what I will talk over some of what you're going to see in this video, but I just had to show it because it's mind-blowing and it's beautiful. So what you're going to see is the astronomers translated the frequencies of the orbits into audible sounds in proportion to the time it takes all of these planets to orbit the TRAPPIST-1 star. You're going to, the furthest planet comes in first with the longest note. And then you'll see the next innermost planet added and the corresponding note. And they'll take this through all 7 of these planets, adding higher and higher pitch notes so that they play one note every orbital period of that particular planet. And in a few seconds here, you'll notice they add a drum beat for every time one planet passes another. The effect is really cool. And eventually, they'll even add some sound to correspond to the fluctuating brightness of the star itself. And you can, the website is in my presentation, so you could go to the website and read all about how they actually manage this and how you can do this with try to do this with other planetary systems and other objects in space as well. So you can see the inner planets pass each other more frequently than the outer planets do. And that's why we're getting more and more drum beats as the movie goes on. just to give you a picture of what this fantastic system is like, this is a plot from a very recent paper of planet density versus the amount of light they get from the star. And basically the bottom line of this diagram is that all 7 of these planets are slightly less dense than the Earth. They're approximately the same size of the Earth. And these colored bars up here show the habitable zone. Habitable zone is defined as the distance from a star where, all other things being right, liquid water, the temperatures would be suitable for liquid water to exist. So in the TRAPPIST-1 system, there are actually at least 2 or 3 planets in the habitable zone. And in fact, this paper, another figure in this paper, explored what, based on precise measurements of the planet's densities, what their interiors might be like. And one possible model is similar to the Earth, but with a smaller iron-rich core than the Earth has. There are also possibilities that these planets don't have an iron core, and there are even possibilities that these could be ocean worlds, that some of these worlds could actually have an ocean layer on the surface that would help account for the slightly lower densities. Now, at this point in time, we can't tell you which model is correct. There have to be quite a few further future observations, but we have those observations planned, and we're learning more and more about these fantastic planets. What's also cool is that the TRAPPIST-1 system may be about twice as old as our solar system. Red dwarfs are incredibly long-lived stars, and that opens up a whole lot of prospects for giving life time to evolve on these worlds. So the Planet Habitability Lab at the University of Puerto Rico at Arecibo actually maintains a list of what are considered potentially habitable exoplanets. Now, I want to caution that potentially habitable does not mean inhabited. It doesn't even really mean habitable at this point in time. It means these planets are of a similar size to the Earth, a similar temperature such that they might harbor liquid water, which is essential to life on Earth. We need a lot more observations. I just wanted to point out that 4 of the TRAPPIST-1 planets are actually on this list, along with the exoplanet that's closest to our solar system, Proxima Centauri b. So at this point in time, I would like to step back and take a look at our knowledge and our ignorance, so to speak, what we've learned over the past few decades and what we don't yet know. So what we've learned is that stars and planets form together in these crowded stellar nurseries. The most massive stars cook up the heavy elements necessary for life and disperse them when they explode at the end of their lifetimes. What I haven't had a chance to talk about are all the complex organic molecules that pervade space. There's a field known as astrochemistry that studies molecular reactions in space. The diversity of exoplanets rivals that envisioned by science fiction authors decades ago. And we're discovering an increasing number of Earth-sized exoplanets. Some are in these habitable zones. If you're interested in some of these questions of life, by the way, I do write a short monthly column for an initiative known as the Clergy Letter Project. And there's an archive of these columns on what's called astrobiology that you can explore. So what we don't yet know, certainly our ignorance exceeds our knowledge. How many planets are actually habitable and inhabited? How frequently does life evolve? How frequently might intelligent life develop? The Earth harbors a number of intelligent species, but to the best of our knowledge, we have one civilization that has developed to the extent where we have symbolic language and the technology to actually think about some of these or explore some of these questions and think about them. So the list goes on. But the bottom line is that we are, from all of these studies, we have good reason to think that most stars in the universe have planets, and many of these may actually be habitable. So I'd like to tell you a little bit about the research projects that would be otherwise impossible to carry out were it not for citizen scientists around the world. Citizen science elicits people from all walks of life around the world to help conduct research projects that require either large numbers of human eyes looking for things in digitized data sets, or in some cases, listening for things. Citizen science helps advance research while at the same time allows people to become part of the process of scientific discovery. The largest and most popular online platform for citizen science is called Zooniverse. Projects span many fields of academic research in both the sciences and humanities. People participate around the world. There are hundreds of publications in top journals in the sciences and humanities. And I spearhead a project. You can go to the website if you're interested and contact me about it. I spearhead a project specifically aimed at engaging faith-based communities in citizen science through this platform. So one more very quick video here.
A brief introduction to the Zooniverse. The way we generate knowledge has changed a lot over the last century. Technological advances are creating huge amounts of data that can be hard for researchers to handle by themselves. The Zooniverse is an online platform that connects these struggling researchers with people all around the world who want to help. Together, these volunteers have contributed to many incredible discoveries and a huge amount of wonderful science, such as helping to sift through 1 million images of galaxies in the first project, Galaxy Zoo. Not only did this help to create the most comprehensive survey of galaxies, having so many eyes look at each single data point led to many unexpected discoveries, including a new class of galaxy that appeared as small green blobs, or as the volunteers called them, peas. The Zooniverse has since grown to include over 150 different research projects across all sorts of subject areas and scales, from the stellar to the subcellular and everything else in between. All of this is possible because of a community of nearly 2 million volunteers around the globe, who together are changing the way that modern research is done. Why don't you explore the Zooniverse today?
So I just wanted to note that citizen scientists do make new discoveries, and I wrote a blog about my latest research paper that the web URL is down here. It's a research paper that was made possible by a discovery by citizen scientists. So in the interest of time, I know we're coming up close to 5 o'clock. I'm not going to go through why you might be motivated to participate in Zooniverse. I think some of those motivations are kind of clear. Among other kinds of projects, Zooniverse has many projects that are based in ecology and environmental justice, and there are many faith communities and interfaith communities that are devoted to promoting ecological and environmental awareness and creation care. So there are many reasons to participate or to consider participating. So I would like to share some reflections and give you a few little tidbits on recommended reading here. So one of the things that my good friend who passed away a couple of years ago, George Coyne, was very talked about frequently was how fertile the universe is. It's very creative. It spawns so much diversity. Creation participates in God's creativity. You could also say that the people create in God's creativity. Phil Hefner, the Lutheran theologian, has talked about this a lot in terms of human beings being created co-creators. Another thing we've discovered across virtually all the sciences is that the universe is interactive and relational. This seems to be an ontological principle, the idea of interactivity, and it's spawning a lot of creative discussions for mutual interaction between scientists, theologians, and philosophers. So this book down here, Interactive World, Interactive God, your previous speaker, Michael Spezio, and I both contributed chapters fleshing out this notion of interactivity and how that can spawn these conversations between scientists and theologians. There are a couple of new fields that have been motivated by the real possibility of extraterrestrial life, as well as human exploration of Mars. And my good friend Ted Peters edited a book called Astrotheology, Science and Theology Meet Extraterrestrial Life. So if you're wondering what astrotheology is, well, a quick definition is that it's a branch of theology that analyzes contemporary space sciences combined with classic religious doctrines such as the biblical creation. Astroethics is concerned with considering the application of ethical principles to the space sciences, particularly to the search for extraterrestrial life, but also in thinking about how we go about putting humans on other worlds like Mars, for example. And these are urgent issues that require a lot of conversations among diverse religious communities and people around the world. Another URL, I wrote a response for those of you who are science fiction fans. I wrote a response to some of the ideas put forth in astrotheology that you can get to through that URL for the journal Theology and Science. There's also a great book called Pulpit Science Fiction by George Murphy, and a new book that just came out by Routledge called Intersections of Religion and Astronomy. I know you folks have a lot to do with your time and maybe can't read all of these things. I just offer them as potential resources. There's also a repository of sermons that have written by various clergy members on this initiative, the Clergy Letter Project. So in thinking about your homilies, there are so many possibilities here, especially when we consider the cosmos. There's so much rich language regarding creation and awe. In the Hebrew scriptures, you find these in the Psalms and in Job. In the Christian scriptures, you find in the Gospel of John, in Colossians, in Ephesians, you find this whole notion of the cosmic Christ. So I suggest that there are a lot of rich ways to explore bringing astronomy and cosmology into your sermons. So I'd like to offer just a few more quotes and then I'll stop for questions. So in God in Search of Man, Abraham Joshua Heschel writes, "The surest way to suppress our ability to understand the meaning of God and the importance of worship is to take things for granted. Indifference to the sublime wonder of living is the root of sin." And I think a very similar thought is expressed by Pope Francis. By stimulating wonder before the profound mystery of creation, faith broadens the horizons of reason to shed greater light on the world which discloses itself to scientific investigation. This website here, Mystery and Awe, is maintained by my friend, retired ELCA pastor, Bruce Bucher, and he offers a whole bunch of resources that explore this idea of awe and wonder in science and in faith. This reference by Michael Iaconelli in Dangerous Wonder, Iaconelli expresses the view that the most critical issue facing Christians today isn't those controversial issues that often divide people within a given tradition as well as across traditions. He suggests that the most critical issue is dullness. We have lost our astonishment. He goes on to say that the church should be full of Christians who see questions rather than answers, mystery instead of solutions, wonder instead of explanations. And as I like to say, science really doesn't solve mysteries, it deepens mystery. So I'm going to put up one last slide here. This is a poem written by a Roman Catholic mother of 8 over 100 years ago, 10 years before the first pulp science fiction story about travel to another solar system, when Alice Meynell wrote this beautiful poem, Christ in the Universe. And here she imagines comparing our gospel with 1 million alien gospels in a universe filled with worlds that have life. So I'm not going to read that now, but you can come back to it and read it at your leisure.